Lighthouse Scientific Education presents a lecture in the gas series. The topic, gas, advanced concepts. Much of this material is at best briefly covered in an average chemistry course. Some courses, however, do venture deeper into these topics, and it is for those students that this lecture is intended. Know what material is expected of you. Material in this lecture relies on understanding of the previous lectures, the basics of gas, fundamentals of gas law, and gas law, one condition. This lecture begins with a brief review of gas basics and a re-examination of the Kinetic Molecular Theory, KMT. That requires a review of KMT as covered in the Basics of Gas lecture, and an expansion of the model. This leads to a discussion on random motion of particles, which is used to describe diffusion and effusion. Graham's law is introduced as a way to quantify rates of diffusion and effusion. As a note, one advanced concept involving gas that is not covered in this lecture is stoichiometry. It is, however, covered in the lecture Stoichiometry Advanced Concepts, which is found in the stoichiometry series of lectures. Any discussion involving gases starts with a review of the four basic properties of gases. They are amount in moles, temperature in Kelvin, volume and pressure. These properties can be viewed from the perspective of energy, which focuses on temperature and pressure. Energy is the central theme of this lecture, and a brief review of it and its effects on pressure is warranted. Motion is a form of energy. Motion energy is heat. While heat is a form of energy, temperature is a measurement of the amount of that heat energy. Higher temperatures reflect greater amounts of heat, which means more motion and generally faster gas particles. And like any moving object, the faster a gas particle moves, the harder it strikes or collides. Fast-moving and harder colliding particles create higher pressure. Pressure is the lens in which gas behavior can be most readily rationalized. Pressure is defined as a force exerted over some set area. For a gas, the force is gas particles colliding with the sides of the container, or any object for that matter. Bottom line, more collisions or harder collisions means more force, which means more pressure. This is the connection between energy and pressure. In the Basics of Gas lecture, we looked at the Kinetic Molecular Theory, KMT, as a way of understanding behavior of gases. In this lecture, we will expand on that understanding after providing a review of what we've already covered. KMT treats gases like they are ideal gases. There are three basic assumptions that make a gas ideal. The opening assumption is that a gas is composed of particles, very tiny ones. For the most part, they are compounds or atoms. The particles are modeled as small hard spheres. They are said to have no volume and do not experience intermolecular interactions. Real gases do have volumes and do experience intermolecular interactions. When dealing with gases, the term volume refers to the space available for the gas particles to roam, and not the volume of the particles. The KMT argues that for dilute gases, the gas particles are separated by such large distances that the volume that the gas occupies is mostly empty space. Gas particles make up such a tiny part of the available volume that the gas can be treated as if it essentially takes up none of the available volume. The volume of the particle is neglected. As for intermolecular interactions, a useful real-world model is billiard balls. They are relatively small compared to the table, and they do not stick to or repel each other. In the previous lecture, Gas Law 1 Condition, deviations to the concept of an ideal gas is covered in van der Waals' modification to the ideal gas law. The second assumption is that the particles in the gas move rapidly and are in constant random motion. More specifically, the motion of the particles are in straight lines and only change direction upon colliding with another particle or some surface. As mentioned earlier, particles speed up when heated. An increase of heat leads to an increase of collisions and promotes random motion. The third assumption is that the collisions are perfectly elastic. In other words, the energy of motion is transferred without loss. In the billiard ball analogy, on a break of a rack of balls, the total energy of the cue ball is transferred into the other billiard balls. No energy is lost due to bending or cracking of a ball. For the most part, these assumptions provide a satisfactory understanding of the model. However, digging a bit deeper, we will find a broader understanding of gases and their properties with this model. As mentioned earlier, energy is a useful viewpoint for the study of gas. The energy of a gas can be viewed from two perspectives, and they give insight to different aspects of gas behavior, but can be united into one picture. The first perspective is using kinetic energy, or average kinetic energy, AKE. It is the average energy of motion of all particles. The term kinetic means motion. The other perspective is with thermal energy, heat energy. It is concerned with total energy of all the particles that make up the gas, and is helpful in viewing the role of mass in motion. We will look at these perspectives one at a time, starting with the average kinetic energy. Here we focus on the energy of motion. Broadly speaking, we know that fast-moving objects have more energy than slower-moving objects. Who wants to be hit by the faster-moving baseball? Also, for two objects moving at the same speed, the heavier one has more energy. Who wants to be hit by a bowling ball? This intuitive understanding has a mathematical definition, kinetic energy, Ke. It is equal to 1/2 the mass, m, of an object times the square of its velocity, v. Speed can be used for velocity in most cases. That definition tells us that the more mass an object has, the more energy it will have. Also, the faster an object goes, larger velocity, the more energy it will have. This is consistent with our understanding of heat as energy. Particles speed up when heated. And since temperature is a measurement of heat, the average kinetic energy is proportional to the measured temperature. We will limit that statement to within any one specific gas. Temperature is a reflection of heat, which relates to speed or velocity, which relates to kinetic energy. Now, to the term average in average kinetic energy. When dealing with AKE, the kinetic energy of all the particles have to be considered. Importantly, in a gas, the particles do not all have the same velocity. Individual particles will not all have the same kinetic energy. Returning to the billiard ball analogy, not all the balls have the same speed coming out of the break. Additionally, when the balls begin to collide with each other, some balls gain speed while others lose speed. Colliding particles will do the same thing. KMT says that the total energy of the collisions is conserved, but it allows for the energy of motion of one particle to be transferred to that of another particle. That is where average comes. For example, here's a graph of the distribution of speeds of gas particles in a sample of the noble gas xenon. The velocity or speed, x-axis, of the individual particles are plotted against the population, y-axis, of particles in the gas with such speed. Another way to say this is what fraction of the gas has what speed. This is a bell-shaped curve. There is a distribution of velocities or speeds. Not all the particles are going the same speed. There are fewer particles, low population, small fraction, with really slow or really fast velocities. The majority of the particles are centered around the average velocity, which is the peak of the curve. In fact, the velocity at the peak is representative of the average velocity of the particles. This velocity can be used, along with mass, to calculate the average kinetic energy and all that implies. It makes sense to use the peak as an average, since about half of the particles are moving slower than the average speed, and half are moving faster. We can use this curve to ask what happens when heat is added to the sample of gas. Adding heat is adding kinetic energy. Having a higher kinetic energy means overall faster particles. That comes right from the definition of kinetic energy. If the energy goes up and the mass of the particles stay the same, then the only way to keep the sides of the equation equal is for the velocity to go up. What should we expect to happen to the peak of the curve if heat was added to the sample of xenon displayed in the graph? The peak should shift to a higher velocity. And that's what we see. A new distribution of speeds with a new peak, T2. Overall, the particles are going faster. With these two curves, we can make a couple observations. The first one is a recognition that heat was added to the sample of gas to get it to the higher temperature, T2. So the average kinetic energy, AKE, of the gas at T1 is less than the average kinetic energy of the gas at T2. That can be seen with a shift in the peak of the curve. As the temperature is raised, particles move faster, and T2 reflects a higher average speed than T1 does. Putting the respective velocities into the average kinetic energy equations would indeed show that AKE attached to T2 was larger than AKE attached to T1. The second observation is that the spread of the curve is increased. The T2 curve is shorter and fatter. With higher velocities come more collisions, and that leads to a broader distribution of speeds. Looking at gas from the perspective of kinetic energy is about the speed of the particles. The other energy perspective is thermal energy. It is concerned with the total energy of the particles. The total energy of a sample of gas at a particular temperature is proportional to the area under the curve. The thermal energy under the first condition, T1, is proportional to the area under this bell-shaped curve. And the thermal energy under the second condition, T2, is proportional to the area under this bell-shaped curve. So the total area under these curves should not be equal because their thermal energies are not equal. Heat energy was added to get the T2 curve. The T2 curve is shorter and fatter, but will have a greater total area. If we were to print out separate graphs of these two distributions and then cut out the bell-shaped curves, the one representing T2 would weigh more than the one representing T1. T2 has more area. Now, let's return to one temperature for xenon, say T1, and reconsider the distribution of particles of a gas from the perspective of mass in the kinetic energy equation, since distribution is dependent on size as well as velocity. Keeping to the one temperature, same heat, we can bring in another curve of a different kind of gas, helium, that has the same number of particles and is in the same size container. Amount, temperature, and volume are the same for these two gases, and yet they have different distributions of velocity. How is that? Well, it's not all about speed. Because they have the same basic gas properties, they have the same average kinetic energy. The average kinetic energy of the xenon particles is equal to the average kinetic energy of the helium particles. One might expect the AKE for helium to be larger since it has a larger average velocity. It is not true because there are additional factors to consider. Keep in mind the equation for kinetic energy, 1/2 mass of the particle times velocity squared. Note that these two average kinetic energies have different size masses. Xenon is much heavier than helium. For these two energies to remain equal to each other with different masses, the velocity squared term in the AKE of xenon has to be smaller than the velocity squared term in the AKE of helium. That is, under the same conditions, larger mass gases have slower average speeds, and smaller mass gases have larger or faster average speeds. They have the same average kinetic energy, but one does it by being heavier, xenon, and the other by being faster, helium. Because they have equivalent AKEs, they exert the same force on the container and therefore produce the same pressure. That is kind of the take-home lesson here. At the same temperature, with all things being equal, all gases produce the same pressure. Some produce the force by moving faster and making more collisions, and some by moving slower but hitting harder due to being heavier. We can take this new understanding and revisit collisions. From the average kinetic energy, we know that gas particles have large velocities. At room temperature, some of xenon's particles will have velocities of over 500 meters per second. At such speed, however, it is not long before a particle will collide with another particle or some other object. Collisions between particles creates what appears to be random motion. Another commonly used term is that the particles appear to be on a random walk. To be sure that we're all on the same page, consider this cartoon that follows just one of the gas particles in the container. It appears to rapidly change direction for no observable reason. But if we were able to track that motion, it would be a series of straight lines in which every change of direction is the result of a collision with another particle or with the size of the container. The path is called a random walk because every particle in the gas will have its own unique set of collisions and its own unique path. There is no knowing where any one particle will end up at any one time. It is random. Some gas behavior can be best understood from an understanding of the overall pattern or distribution of the gas particles taking random walks. There are factors which influence the overall distribution of gas particles, and they include time, amount, as in the number of moles of gas, and the average kinetic energy of the gas. The kinetic energy can be broken down into the factor of speed, or velocity, which is associated with the temperature of the gas, and mass of the particle, which will be found with the molar mass of the gas particles. Time, amount, speed, and mass affect the overall distribution of a gas because they affect the random walk of the individual particles. As an illustration, consider a small collection of gas particles, initially located closely together. An example would be a spray of a room deodorant like Lysol. Now, being a gas, these particles instantly begin moving and wandering about the available space. We fully expect the collection of particles to spread out from its original position. Looking at the spread under different conditions will give us perspective on gas behavior as reasoned from random motion. Condition 1, and we will fill in what those conditions are momentarily. The particles begin to randomly walk about and will disperse over a broad area. This circle roughly gives an area in which the particles could have spread into. If we were to rerun the distribution from the initially closely packed collection under the same condition 1, then a different spread would have been seen, but most likely it would have fallen within that circle. This circle represents the boundary of the spread at condition 1. Now we change conditions, condition 2, and we reset the particles to their original position. Being only concerned with the final position of the particles after the random walk, we see a new distribution or spread of particles. This circle represents the boundary of the spread at condition 2. Removing the particles and only focusing on the spread, we have the spread at condition 2 and the spread at condition 1. With these two spreads, we can ask how factors of time, speed, and mass affect distribution, starting with time. Say that condition 1 was the distribution over a set time, t sub 1, and condition 2 only varied in its set time, t sub 2. Comparing the two circles as spreads or distributions brings up the conclusion that T1 is less than T2. The longer particles have to randomly walk about, the broader the distribution of particles will be. Given more time, the probability that any given particle is further from its initial position is greater. Now say that the two conditions are over the same period of time, but differ in the amount of particles. We will use the variable n for moles to represent amount, and the subscript 1 and 2 to denote condition. Condition 1 has less particles than condition 2. Condition 2 will have a broader distribution. With more particles, there are more collisions, and it is more likely that there are particles that randomly walk much further away than the average particle does. That is just statistics. An analogy is that 25 first graders are bound to spread out further on a playground than 5 first graders. First graders are prime examples of random motion. What should we expect if time and amount are held constant in the two conditions, but that temperatures are different? Remember, the average speed or velocity of the particles is proportional to the temperature. Harder particles move faster. The average velocity of particles in condition 1 are different than the average velocity of the particles in condition 2. This distribution pattern occurs when the temperature, and therefore velocity, in condition 1 is less than the temperature in condition 2. Faster moving particles can move further from their initial position in the same time period. Their distribution is therefore broader. Finally, consider the pattern of distribution in which the only variable that changes in condition 1 and 2 is the mass of the particles. Condition 1 has mass 1 and condition 2 has mass 2. These circles represent the distribution that occurs when mass 1 is larger than mass 2. This is really an extension of the argument made with different velocities. In the previous section, we saw that for identical conditions, a smaller gas, helium in this example, generally has faster moving particles. Faster moving particles travel further. The broader distribution of gas in condition 2 is due to the smaller gas particles having larger average velocities. In the summation of the 4 variables in the two conditions, the spread is larger given more time, more particles, higher temperature, and a smaller particle. This series of comparisons takes us to our final 2 topics. The first is diffusion, which is the expansion of a gas to occupy all available volume. Diffusion is also used to explain the mixing of gases. And then there is effusion. It is the escape of a gas through a tiny hole in its container. Both of these properties can be explained by the random walk of gas particles. Starting with diffusion as a form of random motion. It is defined as the movement of particles from an area of high concentration to an area of low concentration. Diffusion is not limited to gases. We saw diffusion with osmosis. There it is the diffusion of water across the semi-permeable membrane. Still, it is the movement from an area of high concentration to an area of low concentration. In practice, for gases, it is the expansion of the gas to fill a container or any available volume. In this cartoon, there are 2 spherical volumes that are separated by a barrier. Often such a barrier is a stopcock, which can be opened with a twist of a knob. There are gas particles randomly bouncing around in the left volume. The gas fully occupies that volume. The right volume is empty. The concentration of gas on the left is high. The concentration of gas on the right is low. Diffusion is the movement from an area of high concentration to an area of low concentration. If the barrier were removed, the particles would randomly walk about, and after a period of time, they would eventually fill the 2 volumes. Random walking evens out the concentration. There are factors that affect the rate of diffusion, that is, how long it takes for the concentration to even out. Since random walking is at the heart of diffusion, factors or conditions that affect random walking will affect the rate of diffusion in the same way. such as the role of temperature. At a higher temperature, T2 in this case, a gas will have a larger average velocity. It will have particles that on the average move faster than they did when at temperature T1. Faster moving particles will diffuse faster. That is, the concentration will even out sooner. And then there's the role of mass. All other conditions being equal, lighter particles, M2 in this case, will move faster than particles of a heavier gas. We saw this explanation in the section covering the thermal energy of a gas. The smaller mass gas helium, on average, has faster particles than the larger mass gas xenon. Lighter particles are faster particles, and they will diffuse faster. The other topic with diffusion is that when different gases mix, they mix completely. Gases are homogeneous solutions. In this cartoon, two gases are separated into equal volume vessels with a physical barrier between them. We'll say that these two gases do not interact and do not participate in a chemical reaction. The container on the left has a high concentration of red sphere gas particles. The container on the right has no red sphere particles, so its concentration is low, or actually zero. Conversely, the container on the left has no green sphere particles, so it has a low or zero concentration of the green sphere gas. But the container on the right has a high concentration of the green sphere particles. If the barrier between the vessels were removed, the gases would mix and the concentrations would change. For the most part, the diffusion of one gas occurs independently of the other type of gas. In this example, mixing is really two diffusion events happening at the same time. When the barrier is finally removed, each type of gas, through random walking, diffuses from an area of high concentration of its particle type to an area of low concentration of its particle type. When the diffusion is complete, both containers will have the same concentration of red sphere particles and the same concentration of green sphere particles. The gases mix completely. The mix is a homogeneous solution. Since mixing is a combination of individual diffusion processes, it is independent of the type of gases being mixed. They will both diffuse completely, regardless of the mass of their gas particles. Weight can only influence how long the process of mixing takes. The initial concentration of gases also doesn't matter. One of the gases can be at a much higher concentration than the other. Still, both gases will explore all available space and evenly distribute throughout that space. Same with temperature. Higher temperatures will speed up the particles, and that will speed up the process of diffusion, but not change the final outcome. A companion property to diffusion, effusion. Effusion is the escape of a gas through a tiny hole in its container. In most ways, it is really just the diffusion through the tiny hole. To reiterate, what drives diffusion and effusion is the movement of gas particles from an area of high concentration to an area of low concentration, and that will happen through the random motion of particles. A demonstration of the process of effusion has two enclosed chambers next to each other. We will say that they are both completely sealed, even though we can see inside. The volume on the left has a vacuum. There are no gas particles in that chamber, so the pressure is zero. The volume on the right has a mix of gas particles zipping around on random walks. If a pinprick or small hole was made between the chambers, and the particles continued their random walk and random collisions, we would expect some of the gas particles to find their way through that hole. Without a hole, the particles would have simply bounced off that part of the wall. But with a hole there, they sailed straight through. We would also expect to hear that psss sound of a small leak. Effusion is influenced by the same set of factors as diffusion. That can be viewed through the kinetic energy of the gas. Effusion is influenced by the mass and velocity of the gas particles. Adding heat to a sample of gas increases its kinetic energy. Since the mass of the particles don't change with heating, The larger kinetic energy means a larger velocity or faster particles. Faster velocities affect faster diffusion, and faster diffusion creates faster effusion. In this context, faster effusion refers to the time it takes for the pressure of the gas on the two sides of the tiny hole to become equal. That is, enough gas from the area of high concentration has moved into the area of low concentration so that both sides of the tiny hole have the same concentration. From a sound perspective, it would be where that psss sound of escaping gas comes to an end. Higher temperatures drive higher effusion. The other component in the kinetic energy equation is mass. For that, we return to the distribution of speeds for two gases at the same temperature. The atomic mass of xenon is greater than that for helium. Because they are at the same temperature, the smaller gas has higher average velocity and a faster diffusion. Faster diffusion creates faster effusion. Take-home point, smaller particles effuse faster. But how much faster? That understanding comes right out of the kinetic energy equation and is summed up in what is called Graham's law. It states that the rate of diffusion and infusion is inversely proportional to the square root of the molar mass of the gas. Rate in this context can be thought of as how long it takes the process of moving from an area of high concentration to an area of low concentration. Inversely proportional means that the molar mass quantity is in the denominator. The law doesn't look like it comes straight out of the kinetic energy equation, but if we make the argument that diffusion and effusion are proportional to the velocity of the particles, then solving the kinetic energy equation for velocity is an indicator of rate. Going from v squared to v is going to take a square root. The student can either do the algebra themselves or just take it on faith. Graham's law is useful in comparing the rates of two gases. The comparison is done in a ratio. The rate of diffusion or effusion of gas 1 over the rate of diffusion or effusion for gas 2. It is not a particularly pretty equation, but some fraction algebra solves it to a more manageable ratio of square roots of the molar masses, and another algebra step puts both molar masses under the same square root sign, and we have a functional form of Graham's law. This form of Graham's law is often provided to the student, so none of that more complex algebra is really required. The thing to note about this equation is that on the rate side, information is gas 1 over gas 2, but on the molar mass side, it is gas 2 over gas 1. Example of its utility can help add perspective. Say we're given a problem that starts by noting that hydrogen gas is lighter than molecular oxygen gas and should effuse faster. But then specifically asked, what is the ratio of the rates of effusion of these gases? It assumes that the properties of temperature, pressure, and amount are constant. All it's looking for is a comparison of how long it takes the gases to completely effuse under identical conditions. How does the rate of effusion for H2 compare with the rate of effusion for O2? According to Graham's law, it is the square root of the molar mass of O2 over the molar mass of H2. That is the square root of 32 grams per mole, molar mass of O2, over 2.0 grams per mole, molar mass of H2. Units cancel, and 32 divided by 2 is 16. The square root of 16 is 4. The rate of effusion for H2 is 4 times faster than that of O2. The ratio of masses is 16, but the ratio of effusion is only 4. And that ends the material of the lecture. Recapping the lecture. we took a deeper look at the kinetic molecular theory of gases and introduced the term average kinetic energy, AKE. It is the average energy of motion for all particles and allows energy to be discussed in terms of motion. AKE is proportional to temperature, since temperature is a measure of heat or motion energy. Kinetic energy is defined as 1/2 mass times velocity squared. The average KE can be estimated by using an average for the velocity of the particles. And it is an average because for any gas, the particles have a distribution of speeds. This makes sense because the particles are constantly colliding and changing speed. Faster particles have higher kinetic energy. The speed at the peak is representative of the average speed of all particles. If the temperature is increased, then there'll be a shift in the overall distribution of velocities, and that includes a shift in the peak. A higher temperature means a faster average velocity and a broader spread of speeds. The energy of a gas can be looked at from a thermal perspective. That is, looking at all of the energy from all of the particles. It also uses the features of the kinetic energy equation and includes the roles of mass as well as velocity in comparing behavior of gases. In particular, we looked at the distribution of velocities for gases of different masses at the same temperature. That means the two gases have the same average kinetic energy. As such, the gas with the larger mass will have a smaller average velocity, while the gas of a smaller mass will have a larger average velocity. From an understanding of KMT, collisions between particles creates a motion for the particles that appears to be a random walk. This leads to a random distribution of particles. Factors that influence the distribution include how long the particles have to walk, their average velocity, and their mass. With an understanding of random motion, we looked at two additional properties. The first was diffusion. It is the movement of particles from an area of high concentration to an area of low concentration. Factors that affect the distribution of particles on a random walk will affect diffusion. Adding heat produces a larger average kinetic energy with larger average velocities. That promotes faster diffusion. For a given kinetic energy, a set temperature, smaller particles have larger velocities. Smaller particles will therefore diffuse faster than larger ones. The other property was effusion. It is the escape of a gas through a tiny hole in its container. Essentially, effusion is diffusion through a small hole. Therefore, the same factors that influence diffusion will influence effusion and will affect it in the same manner. Graham's law is a way to compare the rates of diffusion or effusion of gases. For any one gas, the rate is inversely proportional to the square root of the molar mass of the gas. For two gases, the rate of diffusion or effusion can be compared by the ratio of the individual rates, which is found with a comparison of molar masses and some math. And that completes our lecture. It is the mass and velocity of gas particles that dictate behavior.